Hello my dear students, welcome back to the St. Joseph Composite PU College, Vijaypur. I'm Rahul, chemistry faculty, and in this video I'm going to explain that what is this graph. This graph is drawn from the Raoults law. It contains huge informations. Let's understand and build this graph and understand that how we can calculate the total pressure of a liquid solutions, which contains the non-volatile components. Let me take an example. Take a container. We need some sort of container here, and in this container I'm going to fill some amount of volatile liquid. Assume that this is the volatile liquid, so here it is the volatile liquid layer, and in that the molecules are arranged randomly. This is how the molecules are arranged. Okay, this is how the molecules are arranged, and these molecules get vaporized, and these are the vapor molecules which are present. These are the vapor molecules, or let me write here the vapor of component. I will term it as a component. Okay, now the mole fraction of this component, because it is a pure component, is there, the mole fraction of component A is given as 1. Why 1? We know that sum of all the components present in a solutions is equals to 1, but thing is that here only one component is present, and because of that reason the mole fraction of component A is equals to 1, because other components are taken here as a 0 components. Now therefore, when the mole fraction is equals to 1, it get vaporized more because only the pure substance is there. It get exposed more to the environment and gains a certain amount of energy and convert into a vapor, and there is equilibrium is established. Now the vapor of the component A can be given as here, that is, or vapor pressure of the component A can be given as P naught A. The naught indicate or 0 indicate that it's a pure component, right? This is one part. So now if I add some other component in that, assume that I'm going to add here some components like B component. The B component is added here. Okay, when I add the B component, the mole fraction of A is less than 1. Yes, why it is less than 1? Because we know that in this we have to minus or subtract the subtract the mole fraction of B. It means that the mole fraction of A is less than 1. Okay, and therefore as I go on adding the component B into component A, the mole fraction of A is decreases. Okay, the mole fraction of A can become equals to 0, when mole fraction of B is exactly equals to 1. The meaning is only the B component is present, there is no A component is present. Like same kind of beaker we have to take and explain with a B component, right? So at that moment we'll take certain amount of pressure. Okay, let the pressure becomes, at that moment the pressure of A equals to 0 it is. Okay, now we have to construct a graph depending upon this observation. Let's go with this. Let me have a line over here, and then let me take one more line here. This is a line along this. Okay, it's a little bit crossed. Okay, along this axis I will take here P, the pressure component is there, it is. Okay, along this axis, and along this axis I will take mole fraction of A. I will take mole fraction of A equals to 1, or here the mole fraction of A equals to 0. That is decreasing here. When the mole fraction is equals to 1, okay, mole fraction is equals to 1. Let me write this pointer. Let me erase this part because we are not. Okay, let me. So now what happens? Mole fraction of A is equals to 1. It means that the partial pressure is very high. Let me take it the P naught of A. Now as the mole fraction is decreasing, mole fraction of A is decreasing due to the addition of mole fraction or component B. Here the mole fraction of A is go on decreases and reaches to 0. At that moment the partial pressure of the pure component is also 0, and therefore we'll draw a line here connecting these 2 points. This indicates the partial pressure of A. The same thing we can explain using some other part, like, okay, let me arrange one more graph here, students. First let me slide it away. Let me keep it here. Now what I'll do that, I will draw one more graph. Okay, this time I will change the position of the graph, students. Okay, now here the mole fraction of B is there, which is equals to 1, and here the mole fraction of B is there, and that equals to 0. Okay, a little bit here I will take mole fraction of B equals to 1, and here mole fraction of B equals to 0. Okay, two components are there. Obviously, when the mole fraction of B alone is there, its partial pressure is taken as PB. Somewhere here I will take. So this is the highest I will take. The vaporization is higher for the B component. The more volatile solvent is there, or the component is there. When the mole fraction of B is 0, then the vapor pressure of the B component is also 0. Let me draw a line over there. This is a line. Okay. Now what I will do that I will combine these two components or two graphs, and let's see what we get. So I will take this graph and then I combine it. See students, what you get. Okay, this is what we get, the graph. This graph indicate that the components, both the components we have taken, right? This is a component of A. When A alone is 1, at that moment B is equal to 0. Somewhere here at the middle point, if you take where the mole fraction of A equals to 0.5 and mole fraction of B equals to 0.5 here, like that. Okay. But only thing is that here the mole fraction of A is when equals to 0, its partial pressure is 0. Okay. So I forgot to write here PB. It's a PB, students. Now what happens when you mix both the components? In the vapor phase, you will see that in the vapor phase we have, along with the A component, along with A component, B component is also present. Both the vapors are present. Now whatever the total pressure is there, that we can calculate using the Raoults law. And what a Raoults law say that? Raoults law is the total pressure created by the, you can say that components is equal to partial pressure of individual gases. Okay. So that partial pressure of individual gases can be calculated by its partial pressure at pure component and multiplied by its mole fraction. So we can combine Dalton's law and Raoults law and write the total pressure. Okay, let me write here regarding this line. So I will join this line. When I join this line, this indicates that the P total it is. P total. And P total can be given as P of A plus P of B. But what is the P of A? The P of A can be given as P of A can be given as P naught of A into mole fraction of A. This is a Raoults law. Okay, and the same way in the PB equals to the partial pressure of B multiplied by that's the mole fraction of B. Okay, when I combine these two, I get here total pressure of the component in a container. Okay, this is all about the graph, students. Now we can make certain observations here regarding this graph. Just look at the graph. When xi A equals to 1, when xi A equals to 1, that equation we have, that one equation we have in the previously, that P equals to P naught A into 1 we have. Okay, that's equal to P naught of A we have. But when the same thing, when xi A equals to 0, in that case P naught or P is equal to P naught of A, and mole fraction is 0 here, and we get here 0 partial pressure, or pressure is not there in that case. Okay, the same thing we can write for the B also. When xi B equals to 1, in that case P equals to P naught B into 1 we can write. Okay, or xi B equals to 0, then we can write here P is equal to P naught B into 0 we can write, and here we get P naught B, and here we get 0. Okay, so therefore we can say that the total pressure P equals to P of A plus P of B, but we can express this as a P equals to, that is a mole that is a P naught A into mole fraction of A plus P naught B and mole fraction of B. This is the equation used to calculate the total pressure exerted by the sum of the components or total components in a solution. Hope you understood this, students. Thank you for watching this.